I will say some things about models, but I will not describe a special model, but I will go into the question how conservative is conservative enough if we are modeling in occupational safety and health. When we are measuring, we are all aware that exposures are variable. We have variability. Although we have standardized analytical methods that are sufficiently precise, we know that if we make one measurement, that is not enough because exposures are not constant over time and place. And so most sampling strategies nowadays propose several measurements in order to cope with this variability. And I want to just give you a short example. These are toluene exposures in a printing plant. In one printing plant, they were taken by colleagues from INRS, by Clerk and Vincent, and published in 2014. And you see 5 different exposure groups. And you see that measurements were taken over a period of 2 hours and 6 hours. And if you compare the range, the factor between the minimum values that were measured and the maximum values, you see that although the groups were defined as homogeneous exposure groups, and although the measurements were taken in one factory, you have for the 2-hour measurements factors up to 64, and even for the 6-hour measurements, you have factors up to 10. So this underpins that exposures really are variable. Now, when we are modeling exposures in occupational health, there's one case we can model them for the use in epidemiological studies, and then we want to model the exposure of the average worker in order to derive dose effect relationships. But if we want to test compliance with our modeled values, then it's a different situation. Because we want to protect all workers, we have to look at the high end of the exposure distribution. Because if we would look for the average worker, and we say, okay, the exposure for the average worker is below the limit value, we wouldn't protect all the workers with a high exposure. So you already see that this variability in measured exposures or in real-life exposures implies also variability should be considered in modeling. So it's important to model not only the average level of exposure, but also the variability. Now, this is already taken into account in quite a lot of models. I have here some examples. The control banding tools, perhaps you would first say, well, they have one value, but in reality, they don't have a value, they have exposure bands, and normally they are 1 order of magnitude. So this factor of 10 is already modeled by these control banding tools. EasyTalk-Tra has a point estimate, but they say it's a reasonably or realistic worst case. So they are modeling the upper end of the exposure distribution. Stoffen Manager gives you the 90th percentile as a point estimate, but you can also have a look at the whole distribution. ART, as we already have seen this morning in the presentation of David, gives you percentiles with a confidence interval, and Texas, a new tool from INRS, gives you the geometric mean and the geometric standard deviation so that you can calculate percentiles that you want to compare with a limit value. So we see that this variability is already used, and I show you one picture from Stoffen Manager, how you see the additional percentiles. You have the whole exposure distribution in a table. You see 4 percentiles, and then you have a graph with more percentiles. And these percentiles are internally calculated from the geometric mean and geometric standard deviation. The standard deviation was estimated during the calibration of the model from the measured values, with which the model was calibrated, but the level, so the geometric mean, is derived from the data you give as input to the model. So my first conclusion, or this is a question, but I think you all would agree that if you ask, should models take into account the variability, we would say yes, they should. And this is really important, I think, for occupational safety and health, because we want to protect all workers, and so we must have the whole variability. Now, what about validation of models? We already heard this morning that it's not only important to develop new models, but it's also important to validate the models, to look, are they realistic? So the first question when you want to validate a model is, what should you test during a validation? And one common answer is that you should look for accuracy and precision. Accuracy means you have the right level, and precision, you don't have a high variability. And often these two are tested by so-called external validation, where you compare model outcome with data from independent source, mostly measurement data. And normally you don't just compare the two values, but you look for several values and then you make a correlation. But, as I said, if exposures show variability and models incorporate this variability, then validation must honor this variability and not just say, I want to have only a very good correlation is important, but I also have to model and to look for this variability if it is captured good by the model. So these are examples from a validation study we did together with TNO, with the measurement data coming from the German exposure database MEGA, and predicted concentrations coming from the Stoffmanager model, in this case of the model for inhalable dust. And when you first see this picture, perhaps you say, well, that model isn't very, very good. But what happens here? When you see, when you have one predicted concentration, let's say you have 1 milligram, in this situation, you have this estimation because you have described the exposure situation. And when you go back to reality, you make measurements in the real world, you see that you don't have one exposure, you have the variability. So why wouldn't you expect, or what you would expect is that if you now compare your estimated value with measurement values, you also have this variability. So when we see the left one is the same figure I showed you just the last slide, and then on the right side you see another example, and perhaps you would have said before my presentation, well, the model on the right side, that's really a good model because I have a good correlation and I don't have high variability. But I want to stress is that in our real world, we don't have these situations without variability. So I would say in the real world, we have a situation like this. And if you look at papers on validation of models, and they don't have only numbers on correlations, but also pictures of the measurement values, you always will find pictures like the left one on the left side. So which methods of validations are used at the moment? I have some examples from validation studies, and the first 4 are for control banding tools, and the method that was used is normally that they look, is our model value, or is the measurement value within the estimated exposure band that is modeled. So they look else, how high is the percentage of measurements that lay within this predicted exposure band or below or above, or they compare it with a limit value, as in the last 2 cases. And they look if the test of compliance gives the same result if I'm doing this test on the measurement data or on the estimated data, the model data. Then the last two examples, two validation studies on Staff Manager, they calculated a correlation coefficient, Spearman's R, and when you look into the paper, the correlation coefficients are like 0.2, 0.4, 0.5, so they are not really so high as you would expect if you have a straight line. Additionally, they calculated relative bias, and in both publications, they used another measure for the quality of the models. They looked what percentage of the measurements was above the modeled 90th percentile. So this is the first try, I would say, to cope with this variability that we find in the measured values. And I think that's important to look at this variability. So my second conclusion, or the second answer, the second question I would also answer with yes is, should the validation of models take into account variability? Yes. So not only during the modeling, I have to model the variability, but also during the validation process, I have to take this into account. And I want to propose a new validation method. I've called it multiple percentile testing. And the idea is that we not only test if 10% are above the 90th percentile or 90% are below the 90th percentile, but we test a set of conditions. So here, if 95% lay below the 95th percentile and 50% below the median. The advantage of this method is that the validation method really incorporates the variability of measurement values. And I calculated this, I tried this method with data from the validation study that we did with the MEGA data and the Staff Manager model. And I have now two of the algorithms used in Staff Manager. On the left side, you see the results for the algorithm for the handling of powders and granules. So these are tasks like filling, mixing, cleaning tasks, so cleaning of dust. And on the right side, we have abrasive processing of wood and stone. So sawing, cutting, grinding, things like that. And in this table, I have in the first column the percentiles, and then in the second column, you see the number of percentiles below this estimated percentile, and then the percentage. And if the model is really good, then if it's the 50th percentile, then 50% of the measurements should lay below the estimated percentile. You see that for the handling of powders and granules, up to the 95th percentile or up to the 90th percentile, the values are lower than the value for the percentile. So the model has a moderate underestimation. And for the abrasive processing of wood and stone, the numbers are higher than we would expect from the percentile. So in this case, we have an overestimation of the model. And the question is now, how important is this over or underestimation? And what I tried here is I calculated a chi-square from this. You can calculate it if you have expected numbers and measured numbers. And you see that in the first case, for the handling of powders and granules, the chi-square is 12.7. That with this number, if we are using a normal chi-square test, we would say that this abbreviation from the expected numbers is not significant on the 5% level. And when we look to the right side, we see for the abrasive processing, the chi-square is much higher, it's 142, and there we have, with a normal chi-square test, a significant deviation from the expected numbers. If this chi-square test is really the adequate test we have still to discuss with statisticians, but this was just to try to look how big is the difference between the tasks. So I come to the discussion. We all recognize in OSH that, or it's often stated that conservative models are required because all workers should be protected. If we want to compare with limit values, it's another case, as I said, if we are estimating for epidemiological studies. But the question is always how conservative is conservative enough? Should we claim that all the modeled values have to be above measured values, but then the people from the companies come and they say, well, your model is overestimation exposure. I don't believe that the exposure is really so high in my factory. So the question is, should we model the 90th percentile, or should we model the 95th percentile? Or some even say we should calculate a confidence limit around the 95th percentile and take the upper limit, and you always get an even higher exposure. And our proposal is that we say when we have a model that considers the variability and incorporates it and covers the whole range of exposure, and we have also a validation procedure that tests over the whole range, then we no longer need conservative model with one single value, which is always an overestimation. So this is my last slide. My final conclusions would be exposure height varies over time between and within different workers in different places. I think you all would agree. This variability is already considered in sampling strategies when we are measuring exposure. So we think this variability should also be considered in modeling, and therefore model outputs should preferentially give you several percentiles or geometric mean and geometric standard deviation so that you can calculate percentiles. And this variability should also be considered during the validation of models. And one possibility for this, considering the variability during the validation, is the proposed multiple percentile testing that I presented here with the example of the staff manager validation study. So thank you for your attention.